Good morning and welcome back to chemistry. Hopefully you guys had a good weekend and that you're ready to rock and roll for this week. We are going to do a gizmo that lasts pretty much this entire week, I think. But it's really cool because it really takes that knowledge that we've gained from learning about acids and bases and pH, and we're going to add in a couple of new chemistry concepts, and it really relates back to that big problem that we were talking about why is it so bad that the ocean is becoming more acidic, right? So the purpose of this video is just to give you an introduction to the gizmo and the problem that they are going to be giving you, and also just a little overview of some of the buttons that you guys are going to be needing to press throughout this week. So when you go into Gizmo and you launch the ocean carbon equilibrium gizmo, it's going to look something like this. So let's go ahead and go through the first couple of things. It says that you are a marine chemist working at the National Ocean and Atmospheric Administration, aka NOAA. Whenever you see an orange word throughout this gizmo, you can click on it and it's going to pull up a glossary. So for example, a marine chemist studies the chemical reactions that happens in the oceans. We'll click next. It says fishermen in Norway have reported that the mussels in the local area are not growing normally. This species of mussel is found in the very cold waters of the Arctic Ocean. Now, mussels, I'm pretty sure that we have them in Lake Michigan, but it's the zebra mussels, and I'm pretty sure that they're not a good thing for Lake Michigan. So that's my only knowledge of mussels. Other ways that you might be related to mussels could be that you eat them. If you like seafood, you might see the little, the black shells and then there's like a yellow goopy thing on the inside. Those are mussels. People eat them. They're a delicacy. But this is the problem, is that mussels are not growing correctly and their shells are not growing correctly. So it says mussels are a type of animal called a marine calcifier. It says that a calcifier are organisms that use calcium ions dissolved in the ocean to build their shells or skeletons. A calcifier uses calcium ions. In case you don't remember, calcium is going to turn into a positive ion. It has a 2+ charge to it. These mussels, with the scientific name Mytilus edulis, I think, are an important part of an Arctic ecosystem. So we get this email that says, "Dear marine chemist, the mussels here are not doing well. Their shells are brittle and they crack easily. They also show signs of abnormal growth. Can you help us solve this problem? Thanks, Shelly Pearl." So here's some pictures that just give you a brief overview of what's happening with these mussels. On the top, this is what a normal mussel shell looks like, right? Rounded, smooth, not chipped, not cracked, pretty symmetrical. Abnormal shell is shown down below. Notice that it's got some rough edges, it's got some cracking. The shape of it is definitely not that symmetrical shape that we originally saw. So the problem could be related to the chemistry of the ocean. It says marine calcifiers need calcium and carbonate ions to make their shells. Now, calcium we already talked about. It says calcium is a positive ion. It has a +2 charge. Carbonate is an anion, which means it's negatively charged. It doesn't say it here, but its chemical formula is CO3, and it has a -2 charge. So it says calcifiers use carbonate as the counter ion to calcium to make their shells. So calcifiers, like mussels, use both calcium and carbonate. When they form their ionic bond, they use that molecule to help them build their shells. It says calcifiers need a healthy ocean equilibrium to have enough calcium and carbonate. That word equilibrium kind of sounds like equal, right? And so we're going to be focusing on how we can find this balance between chemical reactions so that there's no changes in the concentration of molecules so that these mussels can actually grow their shells, while at the same time, the ocean is able to absorb some CO2. Now, throughout this week, this is where we're going to pause on like the introduction part of this. This is one thing that you guys will have to click on and navigate through. It's called the handbook. That's the right-hand tab on this side menu here. These big ideas are the ones that we're going to run through during class time. I think the only one that we don't do during synchronous time is the solubility one, and that one I will just make a quick video about it. But the rest of these, like ocean carbon cycle, Le Chatelier's principle, pH and equilibrium, those are the ones that we'll work through in the afternoon time. So we're not going to use those right now, but let's come back and let's do some more introduction to this big problem. Let's click on shell erosion. So it says the shells of the mussels are eroding or dissolving faster than they're being formed. Mussel shells form slower and erode quicker when there's not enough calcium carbonate in the ocean. So remember, those calcifiers use both calcium and carbonate to form this guy here called calcium carbonate. Most mussels have healthy and eroded parts of their shells. We're going to use the scanning electron microscopy to analyze some shell erosion. So this part of the shell is healthy. If we look at the scanning electron microscopy of that part, we notice that everything is pretty smooth compared to a part that is eroded, and you can see that it's just rough, right? Cracks, roughs, bumps, it's all there. So how has mussel erosion changed over time? If we look at this graph, it shows a very strong positive trend. Data was started being collected in 1995. Most recent data point on this graph is 2020, so it is pretty recent. If we look at the y-axis, it's showing us how much of the shell is typically eroded via percentage. So back in 1995, about 10% of the shell would be eroded. That's normal. But in 2020, we see that now it's nearly 40% of the shell is eroded, which is not healthy for that shell. The question is going to ask, how much did shell erosion increase between 1995 and 2020? If we started at 10% shell erosion and we've ended at 40% shell erosion, that would mean 30 percentage points. Okay, so this is where we stop here. So like I said, throughout this week, we are going to work through the handbook, which gives us some background information on chemistry concepts that we need to help answer this question of what's happening with the mussels. Once we have that background knowledge, then we're going to take a look at collecting some more data about mussel shell erosion, doing some data analysis and interpretation, and also coming up with an experiment that might solve the issue. So this is where we end today. In the afternoon time, we're going to go over this very first chunk that says ocean carbon cycle.